So imagine a world where no organ donors are needed, a world where any type of tissue and organ can be artificially created, function as native without any rejection. Scientists and engineers around the world are currently working to achieve this goal. But what is tissue engineering? Tissue engineering is the area that combines cells, growth factors, and scaffolding materials into functional tissue. For example, in this diagram, what is typically done is that cells are taken from a patient and then incubated to allow them to proliferate or increase in number. They are then transferred into a scaffolding material, typically along with growth factors to allow them to populate this material. They are then transferred to the affected area to then grow normally. But why tissue engineering is so important? It provides functional tissue to restore, maintain, and/or improve damaged tissue or organs. Some examples include skin, blood vessels, tracheas, bones, muscles, among others. There are multiple ways on how tissue or organ can be transplanted into a patient without the need of tissue engineering. For example, if we look into this diagram, we have a few different examples. Autograft, which a tissue comes from the same patient. Isograft, where an identical twin donates the tissue or the organ. We also have allograft, which the tissue or an organ will be donated from another individual of the same species. And finally, we have xenograft, which the tissue or organ comes from a different species. Some example includes vascular graft, like blood vessels, tissue for burn skin replacement, heart valve replacement, among others. Meanwhile, although this is a good step to improve the need of tissue and organs, there's compatibility concerns. If the native or decellularized implant is not compatible, it can create rejection and cause adverse health reactions or even death. The solution: biocompatible materials that can be easily used to create scaffolding material that mimics the native environment. There are various techniques to create scaffolding materials for tissue engineering using biocompatible materials. Some of these include freeze drying, in which a polymer solution and the water are emulsified. They then are frozen, which can be done with liquid nitrogen, for example. That step is followed by a freeze drying to create a scaffold by removing all water from it. Although typically effective in terms of porosity, this process involves multiple steps, and then the use of cells cannot be used during the formation of this specific scaffold. We also have 3D printing, which is typically involve digital instruction to have a scaffold in a specific pattern. While good properties are obtained with different materials like a polymer and ceramics, the use of thermolabile components or even cells are not possible. Another example will be bioprinting. This technique is similar to 3D printing, but it allows the use of cells. A nice advantage is that the tissue and organ can be printed with this technique. Meanwhile, it is really limited in terms of the materials that can be used. And then another final example will be electrospinning, which is the main technique that we will be talking about along all this webinar. It can create fibers based from polymers or emulsion solutions. One of the beauty about this technique is that it can process thermolabile components as it operates at room temperature. Why using electrospun fibers for tissue engineering? One of the main keys is that we can easily mimic the extracellular matrix. What does this mean? If you have your tissue, you remove the cells from it. What is left over is what is known as the extracellular matrix. If you look at the top image, you can see how the structure of a blood vessel that doesn't contain any cells looks like. With electrospun fibers, you can easily obtain a structure that resembles that first image, so decellularized blood vessels. Another advantage of the electrospinning is that a wide variety of materials can be used. With electrospun fibers, you can obtain a high surface-to ratio, which is key for tissue engineering. In terms of fiber diameter, they can be easily controlled through a lot of processing parameters. The typical range is 20 nanometers to 10 micrometers, but higher can be achieved with proper solution development. With electrospinning, we could easily encapsulate any material inside the fiber. This is what is known as a core shell rearrangement, which I'll be talking a little bit in a few slides. For example, if you have a drug that is sensitive to the in vivo environment, we can encapsulate it to protect that drug from the harsh environment. There are other fiber formation techniques like hot melt extrusion, but then they can operate at high temperatures. Therefore, if a polymer blend is used, unwanted copolymerization cannot be controlled. With solution electrospinning, this will be completely avoided. For those of you who are not too familiar with tissue engineering, this image is showing the different stages of an in situ regeneration of biodegradable electrospun scaffolds towards a viable substitute. There are 4 stages that can be described as follows. Implantation of the electrospun scaffold, in which in this case an artificial heart valve and a blood vessel are shown. This is followed with the inflammatory phase, which is characterized by the infiltration of immune cells and formation of a preliminary matrix. We then have the proliferative phase, which is characterized by a second influx of the immune system and tissue producing cells. There's also extracellular matrix deposition, angiogenesis, and re-endothelialization of the construct. Finally, the remodeling phase, where newly formed extracellular matrix is deposited and the inflammation is receded. So basically what this means is that we have the scaffold, the immune system detects a foreign material, secondary cells come in to then proliferate all around the scaffold. Then the cells produce their own extracellular matrix to completely replace the scaffolding material. How does the electrospinning technique works? So the diagram in the left shows the electrospinning setup on its most basic form. We have a polymer solution that is pumped into a capillary needle using a syringe pump or other pumping method. A high voltage is applied into the needle. As the voltage increases, electrostatic forces act in solution. Due to charge accumulation in the tip of the needle, the drop changes into what is known as tailor cone. At this point, a liquid jet is ejected, and due to whipping and bending instabilities, the solvent is evaporating during the process. Eventually, dry fibers are collected into a collector. This process is seen in the image in the middle. And then according to the polymer solution, we can either create electrospun fibers or electrospray particles, which are those 2 SEM images shown in the right. An important aspect about this technology is that it can produce a dry product in a single step. All right, so to introduce you everyone to our electrospinning machine that can be used for tissue engineering applications along to other multiple applications, we have 4 different units that are made in Bionesia. Us, NanoScience Instruments, are the exclusive distributor in the United States. First, we have the LE10, which is a benchtop unit mainly used for basic research and proof of concept. Second unit will be the LE50. This one is a more advanced research unit. It is also a benchtop unit. This specific one can actually be implemented with environmental control. The LE100, which is a larger unit, is able to give unique features for advanced research and development. And then we finally have the LE500, which is aimed for pilot scale and pre-industrial stage. All units allows the tight control of fiber dimensions and stability of fiber and particle production over time. And then also all these units are scalable. A solution recipe can be easily transferred between units without worrying of obtaining different results. So for example, if you acquire the LE10, but then eventually you decide that you would like to increase production, you want to move all the way to the LE500, you can easily transfer that solution recipe and it will work similarly. Since the electrospinning technique is a scalable process, we can easily increase the number of spinning heads along with the size of the machine and this will also increase the production rate all the way to an industrial scale. Another important aspect about this technology is that it can produce a dry product, as I mentioned before, in a single step, which is really crucial, especially when you're using organic solvents. Our units are GMP certifiable and also scalable, allowing the technique to be even scaled all the way to a production plant. As a matter of fact, Bionesia has the first and only GMP certified plant to produce particles and fibers for pharmaceutical applications. This is what you're seeing in the picture in the left is the GMP plant at Bionesia, which is the manufacturer of this Fluidnatek. And then in the picture in the right is one of the products that they are currently making in that GMP plant, which I'll be talking in a few slides from now. The Fluidnatek can be implemented with over 31 accessories that can be upgraded at any time. In the following slides, I'll be showcasing a few of the capabilities for tissue engineering applications specifically. Before I go there, I want to say that home-built units are typically used for electrospinning and electrospraying applications all around the world, including universities and startup companies. This is concerning as it brings some safety concerns like exposure to high voltage. You could be using organic solvents that can be flammable, toxic, and cause health issues if proper ventilation is not involved. If they are used in a university, this could bring liability concerns due to exposing the students and researchers to all these non-safe aspects. The image in the middle shows a typical home-built unit. End user is not maximizing the fume hood space as it needs to be operated inside the fume hood to avoid any solvent exposure to the user. All components are separated from each other, meaning that you need to operate them separately, increasing your chances to get exposed not only to high voltage, but then also to organic fumes. All this can be avoided by using safety-oriented professional equipment like ours, the Fluidnatek. This is our Fluidnatek, the LE100. In all of our units, the parameters are controlled from a touchscreen panel, preventing the user to be in contact with main components during sample development. For example, this image is showing a close-up on the tab that controls the temperature, relative humidity, and airflow inside the chamber. At the right side, just give me one quick second. So at the right side, you can see we're operating right now in the AC mode, so you have temperature, relative humidity, and airflow. But then we also can control the voltage, flow rate, emitter displacement, in this case X, Y, and Z axis, and then we also have the option to control the rotation of the drum or any rotating collector. All units operate outside of the fume hood thanks to the ventilation system that is implemented. It allows all solvents to be properly removed from the chamber during the spinning or spraying process. The chamber is made of stainless steel, aluminum, and glass frames and enclosures. Virtually any solvent can be used. Meanwhile, let's say that a specific solvent that is not compatible with any of this material, either stainless steel, aluminum, or glass, we can easily engineer the unit to be able to operate with that specific solvent. All units have a safety shut-off button in case that the process needs to be completely stopped at any time, which is really important, and it's still increasing the safety. Another feature with the Fluidnatek is that we can create fibers and particles in a single phase, in single phase or core shell arrangement, and even multi-axial, like for example, tri-axial. For single phase, blended or non-blended materials can be electrospun and electrosprayed. Additives can also be incorporated according to the application needs. For example, growth factors can be blended with the polymer solution before electrospinning, or even just added post-processing. This further improves biocompatibility with the in vivo environment. Fibers can have different physical properties by using different solvents. For example, this image in the left, those two images, SEM labeled as A and B. Image A in the left side shows the smaller fiber diameter as opposed to image B. So for image A, we're using acetone as a solvent, polycaprolactone in both. So for A, acetone, for B, we're using dichloromethane. But because one of the main reasons on why we're having that large fiber is because DCM has a low boiling point, so it's evaporating faster, allowing the fiber to be larger in diameter. So that's one of the ways we can control fiber diameter. Core shell and multi-axial structures can also be done with the Fluidnatek. For core shell fibers, this means we're processing two solutions at the same time, one in the core and one in the shell. This is easily done by having a needle inside a second smaller needle, as the right image shows. At the end, we will have beautiful coaxial structure that can be encapsulating or protective any sensitive additive that you would like to encapsulate. A beautiful advantage of the Fluidnatek is that for the LE50 and up, so LE50, LE100, and LE500, we could implement the unit with two independent high voltage sources. This means that two different solutions can be processed simultaneously. This allows the unit to process two different types of fibers, two different types of particles, a mixture of fiber and particles, or even fibers and cells. People sometimes ask me how cells can survive the electrospraying process. Well, the easy answer is that the electrospinning or electrospraying technique typically do not use current in the process, allowing the cells to survive that electrospraying process. So for example, this is a work done by Jan Shu, a friend of mine. She demonstrated that the cell viability after processing them at high voltages, so 10, 15, and 20 kilovolts, control will be 0 kilovolts. So you can clearly see, just give me 1 second until I get this highlighter. So you can clearly see for the control group, you're not exposing it to any voltage. After 1 day, 3 days, and 5 days, the cells are viable, so they are still alive inside the scaffold. But then even though you're processing the cells at 10 kilovolts, 15 kilovolts, or 20 kilovolts, they still grow over time, so they are still maintained viable. So this is really interesting because you can process cells and then make sure that you can populate your scaffold during the sample processing. As I mentioned before, needle-based electrospinning, our Fluidnatek technology operates through needle-based technology using an emitter. Sometimes people call the emitter needle or nozzle, so just in case you have any preference. Depending on the Fluidnatek of interest, we can operate from 1 emitter, 5 emitters, 20 emitters, all the way to 112 emitters. This allows you to increase the throughput by implementing what we call a multi-emitter. So let me get this really quick again. So this will be our multi-emitter. So you can see in this image we're operating the LE500 in this case with up to 96 emitters simultaneously to increase the throughput. In this case, it's a core shell arrangement. Meanwhile, we can also operate with 112 emitters simultaneously. And then again, is in case you want to increase throughput and then cover wider areas during your spinning process. In order to avoid non-reliable results, controlling temperature and relative humidity is really crucial, especially for tissue engineering applications. But why this is so important? As you may know, temperature and relative humidity have strong influence on how the solvent evaporates during the electrospinning or electrospraying process. These two parameters, again, temperature and relative humidity, are strongly influenced according to the location around the world, season of the year. So if your building facilities are not too well controlled, you can easily see dry conditions during the winter, high humidity after it has rained, or even fluctuations during one single day. So for example, I'm actually from Puerto Rico. It rains all the time down there, so humidity can change so fast. So electrospinning without controlling temperature and relative humidity conditioning, batch-to-batch reproduction is never going to be the same. Therefore, if we control these two parameters, you will not only get reproducible results all year long. If GMP certification is needed, this will maximize the batch-to-batch production and reproducibility. So it's not only about controlling temperature and relative humidity. It is also, for example, if you have a polymer solution that requires a specific temperature or relative humidity, more importantly, relative humidity, by using our technology, you will be able to process that sample all year long. The image in the right is a clear representation when the climate conditions are not controlled. The solvent is evaporating so fast that the polymer is partially solidified at the emitter. Secondary jettings may occur, making you to have a wide variety of non-desired fiber or particle. So if you're spinning and then you're having secondary jettings, fiber distribution is going to be really big. So that is not ideal. So what does NanoScience Instruments, along with BioInitia and the Fluidnatek, offers? We offered you over 5 years of climate control expertise. We tightly control temperature, relative humidity, and airflow with ease. While also airflow rate, solvents that are evaporating during the electrospinning or electrospraying process will accumulate if not properly removed from the chamber. Therefore, if they are not properly removed, you will not obtain batch-to-batch reproducible results, as this will affect your spinning or spraying processing. This first image is showing our LE100 unit with climate conditioning and how they are attached between each other. All the air is conditioned in the environmental control unit, so all the air is conditioned in this part of the machine, and then it goes through this flexible duct inside the LE100, and then they communicate between each other, maintaining all the processing conditions really tight over time. The image in the right, it shows our typical range of operation. We can easily operate from 18 Celsius all the way to 45 Celsius. And then in terms of relative humidity, if you look at the lines that are going in an angle, you can see that we can operate through 10% all the way to 80%. So for example, let's say that you are around 25 degrees. That's the temperature that you would like to operate. So you will have the option to control relative humidity from 30% all the way to around 75%. Let's say that you want to, operate at 45 degrees. So that means that you can have a relative humidity from 10% all the way up to 25%. So the unit gives you a lot of flexibility in terms of relative humidity that you can control during your spinning or spraying process, which is really crucial for tissue engineering applications. When you properly control those two, again, temperature and relative humidity, while also removing the solvents from the chamber, you will be able to achieve perfect nanofibers. Achieving consistent fiber production is so important for tissue engineering applications, especially when batch-to-batch reproducibility and similar results throughout the year are needed. These two images are a clear representation of how the microstructure looks when the environmental conditions are tightly controlled during sample production. The image in the left shows all defects or imperfections when conditioning temperature and relative humidity are not possible. So you can have fiber-fiber bundles. You can also have fiber-fiber bonding. You can have fiber beading, more fiber bundles, dust. If you're not controlling really well in the chamber, so let's say that dust from the outside, if you're operating in a fume hood, like an open area, dust can be going directly into the scaffold. So that may affect the patient health, for example, if the sample is not properly sterilized. Meanwhile, when we optimize the spinning conditions, including, again, I want to repeat it because it's so important, including temperature, relative humidity, and also airflow, the microstructure that you will obtain is this one in the right. As you can see, fiber diameter is really uniform and the standard deviation is less than 50 nanometers, which is really, really, really nice. So by controlling these two parameters, along with the airflow, your sample production will be consistent all year round, allowing to have better published papers, which usually people do not include temperature or relative humidity at all. An example of a drug delivery system for regenerative medicine that is currently under clinical trials is the Rivelin patch. This patch is the one that I mentioned before that is made in BioInitia's GMP plant using our technology. A crucial aspect for them is controlling temperature and relative humidity during production because they really need those batch-to-batch reproducibility all year long. For this specific patch, in order to improve drug delivery and regenerative properties, this patch has delivered the drug in only one direction, maximizing drug consumption and usage as it only delivers the drug in one direction. So first we have, how will this be possible? So this is done by using these two layers. The first layer is the bioadhesive layer made of a hydrophilic electrospun fibers, which is containing the drug. The second layer is the impermeable hydrophobic layer. Thanks to this specific layer, the hydrophobicity affects the drug release so much that the drug is only released in this direction. So that also is really important because it's maximizing how the drug is used during release. It's not releasing all around the exposed area, it's only releasing to the affected area. The images in the right shows the actual electrospun scaffold in the first layer. We can also see the cross-section of the patch showing the dense hydrophobic layer, which is this one right here. And then the actual sample patch, how it looks. So the white area will be the electrospun fibers, the cream area will be the hydrophobic layer, and then this will be the patch in action, to say it that way, and how it will be delivering the drug only in one direction. So collectors are crucial for researchers to target specific shapes that can mimic natural tissue. For example, align electrospun fibers in a cylindrical shape were created and seeded with autologous derived stem cells, which is this example shown here. The sample was then used to mimic a tendon and implanted on a horse. The functionality of the tendon actually returned within 5 months, and then the scaffold was fully resorbed within 9 months. So let me get this pointer. So you can see in this image the electrospun graft in a sterile environment. Meanwhile, this is followed by when doctors are cutting the sample to make sure they have the ideal size before implantation, and then the sample during implantation. So this is really cool what this company in Ohio is doing, Nanofiber solutions. Other type of tubular samples that can be done using our system can be also, for example, artificial blood vessels, which a lot of people are working around with this specific application. Polymers, like I mentioned during the question and answer, polycaprolactam, collagen, gelatin, so many others can be used to mimic the mechanical and morphological properties of native tissue. Our solution in terms of collector, since collecting fibers and particles require this collector, sorry that I'm redundant, we offer multiple of those according to your research needs. We have a flat plate collector for either random structures, particles, or 3D structures, which someone was interested in 3D patterning. Rotating drums for aligned fibers, so we can actually control the RPMs. So if we're using high RPMs, we can have aligned fibers. Meanwhile, we can also use the rotating drum. If we use it at low RPMs, we can obtain random fiber orientation. Also, we can have rotating mandrel. This can be implemented for applications like tissue engineering, including the artificial blood vessel shaped graft that can be later implanted in a patient. For 2 of our units, the LE100 and the LE500, we offer roll-to-roll capacity. So this collector can have you can have a substrate in a roll and then slowly be moving that substrate over time. Let me get this spotlight again. So you will have a roll here. This substrate is going to be slowly moving and then collecting on a separate roll, meaning that you will be able to constantly, over time, collect those fibers or particles. Moreover, if you combine this collector with what is shown in this image, the 96 multi-emitter spinning heads, you can even increase the throughput and maximize that spinning time. Another of our collectors in our units will also be the rotating disc. This collector is mainly used to collect aligned fibers due to the small exposed area. Other collectors that are non-standard or even different dimensions that are not our standards, we can even engineer our units to make sure we fulfill your application needs. Anyone that uses a home-built unit knows that creating homogeneous thickness in the sample is really challenging. With the Fluidnatek, this is an easy process that is done by having a meter movement in either 1, 2, or 3 dimensions. This comes back to that question that we have previously. So in the LE100 is the only one that can be implemented with the 3D patterning. So you can actually be controlling X, Y, and Z axis. So if you look from a really low magnification, it seems that it's only one type of fiber, but meanwhile, if you zoom in, you're seeing a bunch of really small fibers. So you technically can be doing like a 3D printing with the electrospinning technique. Meanwhile, another type of orientation that we can do will be aligned fibers and also random fibers. So again, if you're using the rotating drum at low RPMs, you can be obtaining random fibers. If you're using it at really high RPMs, you can be obtaining aligned fibers. So it's really interesting, and then you can target specific application needs for your tissue engineering applications. With all these previous accessories, we can target specific sample properties using the Fluidnatek. When the conditions are right, we can obtain what is known as super aligned fibers, which are these really nice image in the left. So these fibers are typically stronger than randomly oriented fibers, and they can be used for neurological applications. As you may suspect, cell proliferation is affected by fiber orientation. If we seed cells onto random and aligned fiber orientation, we can see the morphology of the cell can change. For example, in random fibers, we see these cells with a geez, I forgot the word now, morphology. And then for aligned fibers, we have elongated morphology. But what does it mean in terms of like an application? So if you have random fibers, the cells are going to tend to move slowly, as opposed to when the fibers are aligned. As a matter of fact, they are 5 times more migratory as opposed to random fibers. For example, this shows the image in the left. Let me get this spotlight. So the image in the left shows the native tissue in the brain. Since we can target fiber orientation with our electrospinning technique, this means that we can mimic that specific native tissue. So for example, this picture, this video in the right. So here we have GFP label cells, which are depicted in green. And they are actually migrating over time because of the alignment of those fibers. So they're actually moving really fast. And then in terms of just a few hours, they're moving up to a few millimeters in terms of displacement. So my video is kind of acting up, but then you get the idea. So because the cells are completely aligned, I mean, the fibers are really aligned, that cells tend to go up and down simultaneously. So they're displacing really fast. Right, with our Fluidnatek technology, there you go. Now you guys can see it. Yeah, so you can see that how fast those cells are moving along the orientation of the fiber. That's really neat. All right, so with our Fluidnatek technology, we can create a wide area for sample production. For example, this image is showing a sample that I actually created here in Phoenix with an average size of 30 centimeters by 62 centimeters in length. Bear in mind that we can actually make larger areas if needed using the roll-to-roll collector. These specific fibers are showing a really interesting property, which people usually call metamaterial. So material that has a property that is not naturally found in nature. To give you an idea, this specific sample thickness is around 0.8 millimeters in thickness. So even though this sample is really thick, you can see how that the sample is becoming completely transparent. One is in touch with a solid structure. That's really neat, I gotta say. So what are some implications for a sample with this property in the medical field? Doctors usually cover a wound area and cannot see what's happening over time. Therefore, they need to remove the bandages and reapply a desired treatment. With a sample like this specific one, in this slide, doctors will be able to see the healing process in real time and will not affect the wound area by removing bandages and even exposing the area to possible not clean environments. It's a kind of like really strong image, so beware. So Renovoderm, along with Nanofiber solutions, create a beautiful electrospun sample called Phoenix Wound Matrix. And then, as a matter of fact, it's an FDA-approved scaffold that is made with our electrospinning technique, with the Fluidnatek. And then in this example, you can see the initial wound on a horse. They then apply the Phoenix Wound Matrix to the affected area. Over time, the tissue slowly heals, and what is really surprising is that even hair is normally grown and no scar formation is seen. So one thing to pay attention is that this wound is really large, and then only in a period of about 4 months that area is completely healed using this Phoenix wound matrix scaffold that is made with our electrospinning machines. This is another example on how the Phoenix wound matrix is used for tissue engineering. A wound measuring about 2 centimeters in diameter, which is depicted at day 0, was covered with the Phoenix wound matrix and bandaged. You can see that over time the affected area is slowly healed. At day 31, the wound is completely healed. Normal tissue has grown, and the inflammatory response has also receded. Using our Fluidnatek technology, we can assure batch-to-batch reproducible scaffold formation for your application needs. This will allow similar microstructure and sample uniformity that will allow normal healing process and consistent results with success. Maintaining a similar thickness around your Electrospun scaffold is necessary to improve and heal normal tissue. This specific example shows how an Electrospun scaffold was soaked with bone marrow and casted in the leg of a horse for 2 weeks. While the tissue was slowly healing for that first 2 weeks, the same scaffold was reapplied after 2 additional weeks, meaning that at 4 weeks of exposure of the healing process occurred. And then you can even see again how the normal hair has been starting to grow. So using this is really, I mean, you can imagine all the applications and implications you can have around just by using this type of scaffold for wound healing and tissue engineering purposes. So as I said, uniform Electrospun thickness is not something that can be easily done. Anyone with experience in electrospinning knows that sample thickness measurement is also not easy to measure. What researchers usually do is that they create the sample and measure it with calipers, which is not reliable, as if you apply too much pressure, it would give you a false thickness. An alternative is by creating the spun sample, then measuring that thickness with a laser micrometer. The only disadvantage that we see is that if the proper thickness was not achieved, you can keep electrospinning, which may make sense. But then if you take it out again, you get the right thickness. What can happen is that you may have delamination from the first time you spin, you measure it, and then the second time you spin. So you can have non-desired delamination. Our solution, real-time sample thickness measurement. So we actually work directly with our customer to engineer this specific accessory to your needs. It is always a high precision accuracy package that can measure over 10 millimeters in range. We offer a traffic light signal as a feature to know the status of your desired thickness. For example, if you want a 100 micrometer sample in terms of thickness, the light will be changing from red to yellow, then green as it reaches your desired thickness. A feedback loop can be implemented with the emitter motion to properly reach the thickness. This image shows the 2 sensors measuring thickness at 2 different locations and how it changes over time. So let me get this spotlight again. So let's say that you're measuring in this area with 1 sensor and this sensor with this area with the second sensor. So you can see how those 2 areas are changing over time. And then let's say that in this area you reach around 100 micrometer thickness, which is your desired one, but then in this area you're around 90 micrometer. That means that since we have a feedback loop system, we can actually make sure that you stop spinning around that area and then just spin in the other side, meaning that you will have a completely uniform thickness all around your sample. Our Fluidnatek technology can also, as I mentioned, one of the first slides, can be upgraded with up to 30 or more accessories at any time. We know some of the struggles for tissue engineering applications. That's why our units can be scaled up to improve production. They can be even certified by current GMP. We also offer HEPA filters and UVC lamps to have a cleaner environment. This image is showing one of our most advanced units, which is called the LE100 Bio. This specific unit is made completely in 316 stainless steel without any crevices or gaps to improve cleanability. It is intended for biomedical and pharmaceutical applications. Meanwhile, but anyone with an interest on it can easily acquire it. We also work towards fulfilling your application needs. We work really close with our customers to make sure we satisfy and meet your application needs. We can engineer our units to your needs, either by using a sterile agent throughout the whole process, applying a vacuum to remove traces of solvents inside the chamber, and even making the unit to work under ISO-5 cleanliness. Lastly, I would like to remember everyone our analytical services. We offer process development and optimization of your current electrospinning solution. We also offer characterization techniques like wettability and contact angle for when the hydrophilicity of your samples are needed. Microstructure analysis can also be performed through our analytical department. So if you're interested in looking at your microstructure, either electrospun scaffold or any other type of material, we can do it using our Phenom desktop SEM. If you would like to have a demo of any of our units, feel free to let us know. We'll be happy to help you out and work with you.